In the last class, we talked about or discussed about the various types of point defects, okay, their configuration, which you had just seen geometrical configuration, how they look like, okay. And then about, we also discussed about the equilibrium concentration of vacancies which we can form in a material. But now what is important is that once vacancies have been generated in the material, okay, these vacancies will be, they are not going to remain static. At high temperatures, they will be moving around. Okay. The migration energy is going to decide what is going to be the net concentration of vacancies which will be present in a material. Suppose some excess concentration of vacancies are going to be there. What is the rate at which the concentration will reach the equilibrium concentration will be decided by how fast or how slow they migrate. Okay. Let us look about the migration energy of vacancies. Okay. When we talk of the migration energy of vacancies, first thing we have to look at it. If a vacancy has to move from one position to another position, what is the mechanism by which this happens? Okay. This is which we are considered a hexagonal two-dimensional lattice in which a vacancy is created in this particular position. Okay. That is, if an atom moves from here to this particular position, okay, then the vacancy might have shifted from this position to this position, correct? For that to happen, the first thing which should happen is that this atom should come and reach a position. That means that the gap is not sufficient for this atom in this hard sphere model to jump to the next site. Okay. That means that some energy is required, okay, or it has to strain that, push the atoms on that adjacent atoms and then jump to that site. What are the ways in which that can happen in a material? In a real material, all the atoms are vibrating around their lattice positions and that vibration increases, okay, depending upon the temperature at which the material is there with respect to its melting point. In such a case, okay, what is going to happen is that during this vibration, it so happens that the atom at the top, this particular atom moves in this direction, this atom moves in this direction, and the thermal vibration which decides what is the way in which this will be moving. So it can so happen that some with less energy it can just move from this, reach this position, intermediate position. When this has reached this intermediate position, from this intermediate position, how is it going to come to this position? There are two possibilities. It's just a probability. Either it can jump back to this position or it can jump into this side. If it jumps into the left side, then the defect has moved. Okay. That is what essentially has to happen. The same thing will happen. We are taking a square lattice where an interstitial atom is put in this position, correct? This interstitial atom, okay, if it has to jump to this side, first it has to come into this middle position where it is occupying, which is at a strained state, from which it can either jump to this side or this side. If it makes a jump to the right side, then we see that the interstitial atom has moved. Okay. So essentially what we can understand looking at this diagram is that it all depends upon the vibrational frequency. There are many attempts are being made when it is vibrating it, but chance that it will succeed is not the same as the vibrational frequency, correct? Now let us look at the same case which I am showing it in a square lattice where it is not a hard sphere model. Okay. So an atom has to, from this atom, okay, the vacancy is that it has to come to this position, and from this position it has to jump, then only the vacancy will shift from here to here, correct? I think this arrow should have been pointed in the other direction. Okay. The same thing can be explained in another way. We can look at the energy diagram. Okay. That energy diagram is that if an atom moves from this particular position to if it comes to an adjacent position, what is it which is going to happen? The same energy will be there, na? That is, it's going to be at the saddle point. But to reach that position, it has to overcome some energy barrier. If it's going to be a substitutional atom, the energy barrier could be very high, or for an interstitial atom, the energy barrier could be small. Okay. Two things which are happening. One is a thermal vibration, which is giving some energy to the atoms, okay, and that makes the atoms vibrate, and it can increase or decrease the gap. That's one. And then another is atom sitting on the adjacent one is trying to jump from here into this side, because that also is all the 3 directions, 6 directions it can equally vibrate, okay, with the same frequency. Okay. Then when that happens, some of the jumps are successful. Okay. Now, this we can try to find out with respect to what is the probability if this is the energy which is required. What is the strain energy which is required, which has to be overcome so that the atom can move from easily from one to the other, okay, to the energy which is available. Okay. It can be written in terms of probability. Okay. And on that basis, if you try to look at it, this is the sort of an expression which we will be getting it, okay, where nu 0 is the debye frequency. Okay. Nu 0 is the debye frequency. Okay. Then there is an exponential term which depends upon the migration entropy, and this is the one which is Em is going to be the migration energy which is required. Okay. This migration energy will consist of one, the strain energy part of it, and another energy also which will come in the picture. Not only the strain energy, it is what is going to be the bond energy between these atoms also will come into the picture. Both of them will decide, okay, the Em. Okay. Generally, it has been seen that this term turns out to be close to 1 in the FCC materials. So, it can be written like nu 0 into this factor. Okay. So, nu 0 is the debye frequency with which the maximum frequency with which an atom vibrates around the lattice sites. Okay. And this in this specific case, this is considered as the height of the energy barrier. Okay. So, this in the literature, the calculations have been done for the various migration energy, okay, from 0.1 to 2 electron volt, and then we look at different temperatures. Okay. What is the rate at which, the success rate at which the atom will jump from one side to another site, or a vacancy will jump from one vacant site to another vacant site. So, this if you look at it, it turns out to be less than 1 frequency, okay, for 2 electron volt, okay, whereas 0.1 is electron volt is the migration energy, it is 2.9, and the same thing if you can see for 2 electron volt migration energy, what it requires is 1.2 into 10 to the power of 5 jumps it will be making it. Okay. This table just shows that what is the sort of successful jumps which will take. This is also going to decide how fast the defect is going to move. Okay. So, the rate at which the defect moves at any particular temperature depends upon the migration energy term. Okay. In the case of vacancy, generally this energy term is also the same as that of what the energy of formation of the vacancy, especially for the case of copper and all this material. Okay. So, it turns out to be rather very high, about 1 electron volt or more. That means that the rate at which the vacancies move is low. Okay. We will talk about it interstitial when we come to that. Okay. Then the next question comes also is that in different lattices if we consider, okay, suppose there is an atomic site and atomic in the cubic lattice, BCC lattice if we consider this is an atom site, at the middle of it I had shown an open circle, what it means is that there is a missing atom is there. Okay. If an atom has to jump from here to reach this position, okay, in between, if you look at it, the layers which are shown with the brown color, that with the brown lines, the triangles which are shown, that shows the different layers. So if this is the A layer, there are two more layers which it has to overcome to reach here. So when it jumps from here to here, it is not one barrier which it has to overcome, two barriers are going to be there. That is, an atom has to be squeezed in that. That is what essentially is being shown here. There is a layer at 1/6 111 position, a layer at 2/6 111 position, okay, and 3/6 111 position is where this vacancy is there. That means that if an atom jumps from here, these layers have to be squeezed when they are vibrating apart. It will jump from there to an in-between position. Then it so happens that the other layers also, the atom positions, they have expanded, moved away. Okay. In such a case, that atom will jump from this position to this position. So in between, there is a point which requires energy less compared to that of the other two layers. This is what it happens in the case of a BCC lattices. This we can find out for various lattices, what will be the, whether it's a one saddle point which is going to be there in the energy or many, more than one. Okay. Whether intermediate stages where it can remain also, where energy is less. Okay. In the case of FCC, if we consider it, here it moves from this particular position to an adjacent vacant site. It's only the atom on the in-between layer. Okay. That's only one layer which the migration energy, if it is able to overcome that migration energy, then it will be coming into that vacant position, it will jump. Okay. So from this simple example, you can see that what is that even in different materials, okay, depending upon the crystal structure, okay, the type of free energy barrier which has to overcome, the shape of the free energy barrier is going to be different. Okay. In this particular view graph, what I am just trying to show is that for various types of crystal structures, BCC and FCC, okay, if a vacancy is created, how the atoms are going to be adjacent atoms. Okay. What is the displacement which takes place to the adjacent atom? Here if you look at it, this first shell is what it means. Positive means that the atoms move closer towards the vacant site. Okay. The negative means that atoms are moving away from the vacant site. Okay. Here if you look at it, in the case of FCC, the relaxation is less, okay, whereas in this case the movement is going to be quite large in the case of BCC, which is an open structure. Okay. The same thing if you look in the case of ionic material. Okay. There, in addition to this movement of atoms, the relaxation taking place, this is controlled by the net charge balance also, correct? Suppose if you look at this case of a sodium chloride, okay, the positive ion, there is a vacancy in this anion site. When there is a vacancy in the anion site, okay, that means that the positive, not cation site, when the cation has been removed from here, now what is going to happen is that this is the one which was attracting the anions to it. Now since that is not there, they will be repelling away. Okay, it is different from what we had seen it in the case of metallic material. Then anions, cations, what will happen is that since one cation has gone from here, they will be moving in. Exactly opposite to what we have seen it in the case of a metallic system, which will happen. Effectively, there are going to be relaxations, and this relaxation is determined by the electronic configuration around the defect, decides how the ions displace from their equilibrium lattice site. Okay. Then, so far what we considered is that only one vacancy is being produced. Okay. Is it that only one vacancy, a single vacancy is produced always, or suppose these vacancies are moving. There's a chance which can happen that two vacancies come close to each other, adjacent sites. Then what will happen? In such a case, if they join together, they can create a where two sites are vacant. This sort of configuration is called as a divacancy. What I am considering, it is a case where this particular atom which is positioned marked as 1, a vacancy is created. Okay. Then vacancy is created in that, to create a vacancy in that site, in this two-dimensional lattice, 4 bonds have to be broken to create a vacancy. Okay. So then this is how it will look like, correct? 4 bonds are broken, the atom has been removed, and I have not shown their position, it may be sitting on the surface somewhere. Suppose at this position, okay, I am trying to remove an atom from this site and create a vacancy. Here again, we have to break 4 bonds, correct? Suppose an atom from this particular position, position 2, okay, I create a vacancy. Then how many bonds have to be broken? Only 3 bonds. That means that an adjacent atom, if you try to remove and try to create a vacancy, it is easy. That means there is a reduction in energy is going to be there. So compared to 2 vacancies, if already vacancies exist, okay, it's always likely that by removal of an atom from an adjacent site, one can create a divacancy. And compared to 2 vacancies moving separately, if a divacancy is created, there is a reduction in energy because 1 bond less is to be broken. Okay. This suggests that always there is a possibility that a divacancies could be produced in the material, correct? So this is what essentially I am giving it here. Now this is the final configuration where will be 2 adjacent vacancies are there, okay. So if independent vacancies, we are creating it 2 vacancies, 8 bonds to be broken. If it is an adjacent sites, we require only in a 2-dimensional lattice 4 bonds only has to be, not 4, it's essentially 7 bonds to be broken in this case to create a divacancy. Okay. So using this information, one can calculate what will be the concentration of vacancies which are going to be there. So what will be the formation energy of the divacancy? 2 vacancies to form independently, what is the formation energy? Minus, okay. So if 2 vacancies to be formed, this is going to be the formation energy twice minus EB is the energy for 1 bond to be broken. So this is what is going to be the net free energy which is required, for formation of a divacancy. Okay. Similar to a vacancy, for which single vacancy we have looked at the concentration of the defect, we can look at it in this case also. So the number of vacancy concentration will be proportional to exponential minus twice EF minus EB by KT, correct? And then we know for a single vacancy what is going to be the value. Okay, similar formula is there. Okay, substituting for EF by KT, that terms, and doing some algebra, we will be able to get some ratio of the divacancies to the single vacancies. Okay, this is given by this formula, which depends only on, in this specific case, the form in which it is written, on the binding energy, that is the energy which is required for breaking of a bond. Okay. Q is one term, depends upon the entropy of formation of defects or divacancies. Okay. This ratio, if we try to write it, okay, this will finally turn out to be that ND to NE, that is a single vacancy, equilibrium concentration of vacancy to a divacancy, this will turn out to be, okay, depends upon the energy of formation of a vacancy, okay, minus the one which is the energy which is required for a single bond to be broken, okay, or the bond energy. Okay. Generally what has been seen is that this ratio turns out to be less than 20%, close to melting point, where the defect concentration of single vacancies itself we consider to be about 10 to the power of -4. Okay. Suppose 3 vacancies join together, then what will happen? Still there can be a reduction in energy could be there, but at the same time when you look at this, that energy term becomes very large, correct? Yeah. Overall energy terms become large. Because of that, the formation energy of a divacancy is as such high compared to that of a single vacancy. So the number of divacancies which will be produced will be less. Similarly, the trivacancies will be less, but still there is a probability, but that probability increases as we raise the temperature. Okay. What is going to be a consequence? Whenever we look at a diffusion equation, we say that this is the rate at which an atom diffuses, okay, and try to find out how the particular phase transformation is going to take place on that basis. When these defects are present, their movement is much faster, because of which the rate at which the growth rate takes place of a precipitate, okay, that could change a lot. Okay. So it is not only that at single vacancies, both divacancies, trivacancies, all these things also do participate and control the kinetics of the reaction. The kinetics of the reaction can change. So if we have to understand that, we should know about the concentration of these defects also which are being present in the material. Okay. Now I will talk about, so far we talked about only vacancies. Interstitials, just a configuration we have looked at it. What are the types of interstitials which can, what are the equilibrium concentration these interstitials can have? That is what we wanted to discuss. Okay. What are the type of interstitials which can have? Self interstitials, okay, and impurity atoms also could occupy interstitial positions. Okay. As I mentioned earlier, okay, then what are the other information which we require is that how are these interstitials produced? Okay. The way in which these interstitials are produced is one, okay, they can be produced as a Frankel defects during ion irradiation or during deformation, okay. Also these interstitials could be produced, because especially when creep process takes place, okay, either it is climb up or down, depends upon whether a vacancy is emitted or an interstitial is emitted from that site. Okay. These are all other ways in which these sort of defects could be produced in the lattice. Okay. And another thing also which I mentioned is that when vacancy is created, it is essentially removing an atom from a specific lattice site, but when we put an interstitial, okay, it can occupy any particular position, and not only that, that from there it can jump to many not only equivalent, non-equivalent positions are also available in the lattice, to which the interstitial can jump. The probability of that occurring is some finite value is there, though it may be negligibly small in some cases. Okay. So here what we are considering it is just what is the way in which interstitial, what is the position, and if you put a self-interstitial atom, okay, or an impurity which has that same size, okay, or a smaller size, if it has to occupy, what position it can occupy in the FCC lattice. Okay. There are interstices which are available, or octahedral interstice sites are there. Okay. These are, especially if you look at the gap in the center of the lattice, okay, or tetrahedral sites are there which correspond to, if each of these cube you divide into 8 smaller cubes, okay, the center of each of that cube will be the tetrahedral sites. Okay. There also an atom can occupy, the interstitial atom can come into that position. Okay. Now anyway, if we consider one of these phases here, if you look at this 100 phase, if we show, This is what essentially we are showing how the atoms are going to occupy positions. If an interstitial atom is introduced into it, the position which the interstitial can occupy is being shown in this. Okay. Now what is going to happen is that this interstitial atom position, if you look at it, the adjacent atoms are very close by. Okay. So the bond energy, if you look at the repulsive force, will be very high. So these atoms will be repelled. Okay. So this is at a configuration which is energetically, if you look at it, is a very high energy configuration. If by somehow or the other, if the atoms can be moved a little bit relaxed, so that the distance between the atoms could be increased further, then in that configuration there could be slight reduction in energy of this defect. Okay. That is what essentially is being shown in this next one. Here we can see that instead of it, this atom is pushed a little bit here and this atom is also moves a little bit here. Now you can see that these two atoms are occupying positions where overall, okay, the separation between the atoms have increased. Okay. This is the sort of configuration in which interstitial can exist. And in the last 10-15 years, people have done a lot of computer simulations, okay, on the material, and they have seen that in fact this sort of configuration is energetically quite stable in the case of FCC material. Okay. And another is also that when we put an interstitial to this position, okay, it strains the lattice quite considerably. Okay. So the energy which is required for formation of this interstitial is going to be very high, because the energy which you have to push the atom into that interstitial site is very high. So in copper especially, it has been seen that it's about 3 to 4 electron volt. Okay. Now, since it's at a high energy configuration, with a little bit of energy it can move from one position to another. So the migration energy which is required is that already the strain energy term is so high that it's trying to push all the atoms further away. So it is to jump from one position to another position, from this position to an adjacent position. Okay, this is an unrelaxed configuration. The relaxed configuration will be pushed apart so that it can easily jump onto it. So that means that the migration energy which is required is always less. So interstitial requires less migration energy, okay, compared to vacancies. And in the case of copper, it's on 0.1 to 0.3 electron volt. That means that these defects can move really fast. Okay. This is the reason why you see that in most of the materials, interstitial defects, when they are present, like when we do an irradiation, okay, vacancies and interstitials are produced. Vacancies move about slowly, the self-interstitials move very fast, and they can come to a surface. Okay. So seeing self-interstitials is going to be more difficult, and that's one of the reasons why we always see the vacancy concentration is the only thing which we see in the material, right? Most of the samples we don't see interstitials, because interstitials, when they are generated, they move so fast. Is it clear? And if you consider the type of defects which are going to be there in the BCC material, okay, in the BCC material, this is the position where octahedral sites which the interstitial atoms can occupy. One is in this position, another is in this position on the edge, and this is on another position is at this edge. Okay. Then the various edges you can occupy, and this is the tetrahedral position. Okay. You assume that an atom is occupying a position like here. I think it is better in this specific position. Okay. When it occupies that position, here again the separation between the atoms, if we see it, it turns out to be small. If it pushes these atoms a little bit, Okay. It can choose a configuration where the separation between the atom has increased considerably. Okay. This sort of configuration is possible. Okay. There is another configuration which has been seen in many ordered alloys. Okay. Yes, not ordered alloys, in disordered alloys, but as during irradiation experiment, is that if an atom comes into it, there is a row of atoms. Okay. That is essentially what it is going to be there, is that if there are atoms are all occupying at some specific separation, if we introduce one atom here, it is going to move the separation row layers. Okay. This atomic positions separation has reduced, okay, because one atom has been pushed into that position. This sort of configuration is called as a Crowdian. Okay. This is one type of an interstitial configuration which has been seen in the material. That is what you can make out that compared to vacancies, now there are many types of configurations in which the interstitials can exist in crystalline materials. Here what I had shown is that though this is the simple configuration which we considered initially, but what is the final configuration which actually has been seen in the real systems is of this type. Okay. Not what we earlier started about the defect configuration. Okay. Now, let us look at, suppose we wanted to find out the concentration of the defects, okay, both for interstitial as well as vacancies. Okay. What all information which we required in the case of vacancies, what we require is that what is the concentration of the vacancy which is going to be there, okay, and its formation energy and the migration energy. If this information is available, we will have complete information about how much of the defect will be produced at each temperature, okay, and how they will, and their kinetics. Both the information we will be getting it. Okay. There are many experiments which could be done to find out this concentration. One is positron annihilation technique, then another is thermal expansion and X-ray diffraction could be used to find out that information. Resistivity is another technique which we could use it. Resistivity or conductivity, both it's the same, and similarly that conductivity could be used to find out the concentration of defects in ionic materials. In the case of interstitial impurities, we have an elastic relaxation is one, and another is internal friction. I will talk about all these things, okay, each one of them. But first let us take the simplest and the one which gives precise information about the vacancy formation energy. Okay. What is it which you have to do it? This is using thermal expansion and XRD measurement. Okay. Suppose we take a sample and heat it. What happens then? The sample will expand. That is, if a sample is a perfect sample also, which does not contain any defect, it has to expand. In addition to it, vacancies are produced. So, when an atom comes to a surface, this also gives rise to relaxation. This also gives rise to expansion of the sample dimension. So, not only just the thermal expansion which takes place, in addition to it, vacancy creation also gives rise to expansion, right. So, look, the thermal expansion gives this information. Suppose I try to, this what will happen is that at any particular temperature, wherever, whatever be the temperature we are considering it, when a vacancy is created, as I had shown earlier, some of the atom positions, the neighboring atoms will come close together. So, there is going to be a relaxation. That relaxation, what it will do? It will give rise to a slight reduction in the expansion parameter, correct? So, what we measure as the thermal expansion is the relaxed change created due to the vacancy, correct? So, if you wanted to get this information, if you do an experiment which involves thermal expansion and another is with, if you do an X-ray diffraction, we can find out the small changes in lattice parameter. Those small changes in lattice parameter are coming due to strains which are introduced due to these defects. Okay. So, essentially what we are trying to find out is that is what this expression says, that if we look at the concentration of the vacancies which are going to be there, okay, that depends upon the volume change which is going to be there plus the delta V by V, the volume change due to the elastic strains which are introduced into the lattice. Okay. The thermal expansion give one value and this relaxation we can get it from XRD. If these two data are there, then we can find out the concentration of the defects very accurately. This is what the simple principle which is involved in this experiment. Okay. So, these are all the terms. So, then from elasticity consideration, we know that the lattice parameter change itself will be equal to 1 by 3 of the volume change in the strain energy term. Okay. And similarly, the thermal expansion delta L by L will be equal to 1 by 3 of the volume change which is going to take place in the thermal expansion. So, substituting all these things, we can find out that by measuring this delta L by L and delta A by A, we can get information about the concentration of the vacancies, the lattice. But what is essentially important is that precision. What is the concentration of vacancies which we are looking for? It is around 10 to the power of minus 4 at best or much lower than that. That means that the precision with which delta L by L has to be measured and delta A by A has to be measured is going to be very high. That is what the experimental difficulty. Otherwise, this is a very neat, simple experiment with which we can get information about the defect concentration in the material. Okay. So, here what is being shown is that the plot of delta L by L versus temperature. Okay. It is being shown taken from from Siemens and Baluffi's work. Okay. Here if you see it at low temperatures, both of them are matching. At high temperatures if you see it, delta L by L, okay, is always shows a higher value compared to that of delta A by A, correct. That is because when a vacancy is formed, okay, there is going to be a relaxation which is going to take place. That relaxation is essentially a contraction. So, it shows a value which is lower, whereas suppose it is an interstitial which is going to be there, then it will always strain the lattice and that will add to a relaxation. So, in that case the delta L by L will be lower and delta A by A will be on the other side, higher side. That is what it will take place. Okay. But from this plot, if we plot this one n by n versus 1 by t, we can get information about only the formation energy. Okay. We can't get any information about the migration energy. Okay. If we have to understand about the kinetics of diffusion or the diffusion characteristics, we should know also that how fast that vacancies move. Okay. That information cannot be obtained from this simple experiment, for which we have to do, okay, experiments which involve essentially resistivity is another technique with which it could be done. Okay. Similarly, that other technique, the positron annihilation technique, could be used to find out the vacancy concentration. Okay. What I will so suppose we consider the resistivity of a material. Okay. The changes in resistivity which takes place in a material depends upon the lattice vibration, okay, that is phonon scattering, the electrons. Then it also occurs due to changes in resistivity due to defects which are scattering these electrons, correct. So, both of them are responsible for it. So, essentially if you try to find out the defect itself, we will try to know what are the types of defects which we can have, interstitials, okay. Then we can have dislocations, Okay. Then we can have impurities, which also can contribute to resistivity changes, then vacancies. Okay. In any material, the way we can assume is that if we are doing experiments on a particular sample, in a quenched sample, if you have quenched it, the defect concentration remains the same. The type of material which you have taken, the impurity concentration remains the same, that will not change. Only change which can brought about in the resistivity is only due to the vacancy concentration variation. Okay. That is essentially what is the assumption which is being made, and that means that if we have to do that, then the lattice contribution also is contributing to resistivity. That could be quite high. If you wanted to get that information, we should do this experiment at very low temperatures. That is, if we do this experiments at liquid nitrogen or liquid helium temperature, okay, then the contribution which is going to come from the lattice vibration could be reduced considerably, and then we can easily, whatever is the resistivity change which is coming, and not only that, if you do it at the same temperature, okay, then what we can do it is that we measure resistivity of the sampled row, okay, at a particular temperature in an ideal condition, which shows this is what the resistivity, okay, only from the lattice vibration plus the defects which are present. And if it has been a sample which has been quenched, it contains excess vacancy concentration. If we measure the resistivity at the same temperature, this will be rho plus rho v, because all other defects are going to be, if we find out the difference, that difference will give you, okay, this difference will give you what is going to be the resistivity change which is going to take place only due to the defect which is present at that temperature. Okay. This is the philosophy which is being used, okay, to find out, okay, the vacancy concentration. Okay. What I will do it is that about the details of this experiment and the other experiments, we will talk about it in the next class.